This is the 2010 Waves paper for Level 2 Physics. Question 1 is on pulses. Janet ties a rope to a pole and sends a pulse down the rope as shown below. Draw a diagram in the space below to show what happens to the pulse after it reflects from the fixed end. Okay, this is our hugest clue, that it's a fixed end. Include an arrow to show the direction of travel of the pulse. Okay, so at a fixed point, which we might call a node, there is no freedom for the wave to move, and the rule here is that there will be a phase change. So the phase will change. That means there's a 180 degrees phase shift on the reflected pulse. So the pulse is going to be reflected on the underneath, just as a rough drawing. It'll look something like that and going in that direction. However, you can see that we've got an asymmetrical shape to our pulse. So that means it's not the same on both sides. You can't cut it down the middle with a mirror line and reflect it the same on both sides, because this leading edge is long and then we've got this sharper tailing end. So as this pulse comes out, we're going to have that leading edge long again and then the sharper tail end. So it'll be the same. Now because it's fixed and not going into another medium, we should get effectively 100% energy transmission, so the amplitude will be the same. So there's a number of things the same, amplitude's the same, wavelength's the same, but the thing that's different is this phase. So let's see if we can draw this. Remember, with the tailing end, because we're drawing it back to front sort of, the tailing end, since it's going that way, the tailing end is the steep side, and then the leading edge is that flat side, and then it carries on down. Okay, so if we were to sketch the wavelength in, it's a good idea, if you're not as great at drawing like I am, would say that the length of the wave or the pulse, to be honest, is the same, and to be honest, where did that come from? And the amplitude is also the same, unchanged. Okay, moving on down. Describe the changes that take place to the following parameters after the pulse is reflected from the fixed end. Well, we've seen speed hasn't changed medium, so it's going to be the same. And frequency is a little bit odd term, because when we're dealing with a pulse, it's a single burst. So yeah, frequency, this is a very, very odd question because of that. However, what you can assume is that it's going to be, if it was a wave in the same medium, because the speed's not changing, the frequency is also going to not change, so it'll be the same as it was on the incoming and outgoing. Okay, C. Janet and Sophie hold two ends of the rope that is stretched between them. They each send a pulse in opposite directions along the rope. The pulses are of equal width, and the diagram below shows the two pulses travelling towards each other. Okay, so the equal width, so we can see that, oops, I'm using the wrong tool, there we go, the wavelength, if we talk about the wavelength of a pulse, is still the same. Pulse A is 10 centimeters high, so this is 10 high, and pulse B is 4 centimeters high, so this is 4. Okay, they've got 4.0, 10.0. We should bear that in mind with the SF that they're giving us, the significant figures. Describe and explain the observations of the pulses when they meet and when they eventually pass each other. So there's there's 4 parts to this, if you like. There's a describe and an explain part, the observations of the pulses when they meet and when they pass. So describe and explain for one point, describe and explain for the second point. Okay, so the description for when they meet, there'll be a single, oh hang on, they're on opposite sides to each other, but there will be a single peak or pulse or whatever you like, which will be the sum, is that symbol for sum, the sum of the two peaks. So it will be, but because one's negative, the B pulse is on the bottom, we'd call that negative by naturally, I'd say. It's going to be 10 minus 4, so it'll be 6 centimeters high. That will be that peak, and the wavelength unchanged. Of course, as they're slowly meeting, they would you would see a gradual merging of these waves, but we're talking about the exact point where they meet, when they're occupying the same point in space on that medium, on that rope. So that's to describe the, that's why I say it looks like that, and the wavelength's unchanged, and the explanation is because the peaks have added. Peaks added, as I was saying before, with B as a negative. And I don't think you really need to explain the wavelength. That's sort of kind of obvious. It's you could say it's a property of the wave that it maintains its wavelength. But anyway, the second part, I'll do this in a different colour so that it's a bit easier to see. So the second part, what happens when they go past each other? They essentially swap positions from the original. And so that this one is now here and this one is now here, and they're still continuing in the same direction, same amplitude. Same direction and the same amplitude. Okay, so the explanation of that is that the two waves, remember the property of a wave, or one of the definitions of a wave is its energy being transferred from one place to the other via a medium. In this case, in this case is a medium. Light is the exception to that, which has no medium. But we have that energy has just passed through each other. Or the waves, you could also say the waves have passed through each other, and continue on. I guess that's a close enough explanation. You get the picture anyway. Moving on. D. Janet and Sophie tie two different ropes together. Now this is where we get just a little bit trickier. The ropes are of different thickness. Different thickness is akin to different optical density, that is, they'll have different speeds and perhaps different frequencies in there because of that speed. But anyway, moving on. Janet sends a pulse along the rope towards Sophie, and we can see it in there. The speed of the pulse in the rope is 4.5 meters per second, and its wavelength is 12.4 centimeters. The wavelength of the pulse as it travels through the second rope is 8.6 centimeters. So we've got a wavelength 1, and we've got a wavelength 2, and we've got a speed 1, and the question is calculate the speed of the pulse in the second rope. So that's going to be our speed 2, which we're trying to work out. And here's our kind of dividing line. This side is 1 and this side is 2. Right, so there is a formula which you can use for this. The formula revolves around the understanding of the properties of the medium, and the heavier the medium, the slower the velocity, and excuse me, and the shorter the wavelength, because the frequency must stay the same, and it's just matching up with v equals f lambda. But anyway, that the reason I say that is it's important to understand where these formulae come from. You shouldn't blindly use them. You should have an understanding of what they mean. So the formula in this case anyway is v1 over v2, which will equal lambda 1 over lambda 2, because as you change medium, the ratios of the velocities and the ratios of the wavelengths are equal for the changes. So we can just simply plug our numbers into this equation and rearrange for v2. In fact, we might rearrange for v2 to start with. So v2 is going to equal v1 lambda 2 over lambda 1. So I've just cross multiplied by lambda 2 and cross divided by lambda 1 and then cross multiplied by v2. You can go and ponder that one a little bit. I've got to get you thinking just a little bit, not spoon feed you too much. Anyway, we plug in those numbers. V1's 4.5 times lambda 2, which is 8.6, divided by 12.4 lambda 1, and when you plug those numbers in, excuse me, you end up with V2 of 3.1. Now, how many significant figures should we give here? We've got 2SF for this, 2SF for this, 3SF for this. The least number of significant figures when you're multiplying and dividing, as we've done in this equation, is to use 2 in this case, so 3.1 is fine. meters per second. And that's our answer. There's alternatives as well to how you could calculate this. You could, for instance, use V equals F lambda to find the frequency, because the frequency will be unchanged, and that would be V1 lambda 1, and the frequency is unchanged. And then you go V2 equals F lambda 2, and you can plug in F again and plug in your known wavelength to find your velocity. But it amounts to the same thing, because this equation uses those common ratios which result as the frequency, as a property of the frequency not changing. And there you go, that's the end.